This is a demonstration of the recently completed B-C register card. I'll start off with the demonstration of the card itself and then move on to showing it hooked up to the completed ALU cards, all fitted in the computer's enclosure. For the B-C register card, we have the status LEDs down the front. The left 10 display the B register status and the right 10 the C register status. Within each register, the leftmost yellow LED shows when that register is being loaded, and the following green LED shows when that register is being selected. The following 8 LEDs show register bits 7 through to 0. Moving up the card, we have the register bit relays. Each relay holds a single bit value, and as with the LEDs, the left-hand group of 8 relays are for register B, and the group of 8 on the right are for register C. Moving further up the card, we have the gating and control relays. The outer group of 4 relays gates the data bus in and out of each register, while the inner 2 handle the register load operation. At the top of the card are the connectors. From left to right, we have the ALU B-C bus, which this card permanently feeds from the B and C registers. Next up is the data and control bus. This card is only interested in the 8-bit data bus values, which can be loaded in and selected out from either of the registers. Next is the Z control bus. This is where the load and select register commands are taken from. And finally, at the far right, there is a usual 12-volt power supply socket. For testing this card, I've made a few tweaks to the breadboard seen in previous videos. Now that I can work directly with the data bus, I don't need the left-hand switches. So whereas previously the left switches fed input B and the middle switches input C, now only the middle switches are needed to hit the data bus directly. The data bus also passes through the LEDs on the right, but this time I've replaced the usual multicoloured 12-volt LEDs with a regular bar graph display linked up to a 1 kiloohm resistor array. This will pass around 10 mA through each lit segment, which is well within limits. Following the ribbon cables back past the register card, we have the usual test board, which this time is feeding the Z control bus for loading and selecting the registers. The Z bus connector is made up of 2 rows of 10 pins, but is perched on 2 rows of 8 pins, and so because of this, for the middle row of buttons, the leftmost is actually the second pin on the connector, not the first. The buttons from left to right are Load B, Load C, and then the next 2 have no function, and then it's Select B and Select C. Following off to the right of the test card, we end up at my bench power supply set to the usual 12 volts. I'll start off by switching on the power supply and setting all bits on the data bus. I can now load register B and then register C. If I now clear the bits, I can select the contents of register B and C back onto the data bus. With all bits off, if I load register B and then C again, this clears the values held. Next up, I'll set an on-on-off-off pattern into register B, and then an off-on-off-on pattern into register C. Again, I can select the contents of each register back onto the data bus. That's pretty much it for the regular functionality, but there is one oddity that the design of this register has. If I set bits 5 and 6 on each registers first, usually when selecting from the register, the data bus will be clear, but if I set bits 0 and 1 on and then select the registers, something odd happens. As you can see, bits 0 and 1 have backfed into the register, and that's meant that following the select, those bits are held on in the register. Effectively, this has performed a logic OR on the register contents. This issue was expected, and actually in normal use the data bus wouldn't have two things on it at the same time, and actually if an OR operation was wanted, you'd normally do that through the ALU. Last thing to test is the B and C ALU feeds. I'll set the same patterns as before, and then switch the data bus cable over to the B and C outputs. It should then be possible to show C and then B on the bar graph display. So, that's it for the BC register. Let's move on to hooking it up with all the other cards to test everything built so far. So, here's the enclosure with all the cards completed so far. You might have noticed that the video lighting has changed quite a bit, and that's because this is one of those rare videos where I've taken it to daylight, whereas the first half of this video was at night with the lights on. Starting from the right, we have the logic card, arithmetic card, control card, and then the new registered BC card. Each card has the various status LEDs down the front, and starting with the logic card, we have LEDs for each of the 5 8-bit results produced. Next on the arithmetic card, we have the 8-bit add or increment result with carry in and carry out LEDs. On the control card, we have the 3 to 8 function decoder input and output on the left, and then the condition register status on the right. And finally, on the new register BC card, we have the B status on the left and C status on the right. Over to the right of the card pack, we have the same testing board used earlier. I've made yet more tweaks to this, and the keen-eyed of you out there might have noticed I've flipped the dip switches around so that bit 0 is on the right, running through to bit 7 on the left. The control bus ribbon cable comes in on the left and is operated by the left bank of dip switches. In this case, switch 6 and 7 select register B and C respectively, and switch 2 and 3 load registers B and C. The data bus comes in on the middle bank of switches, and then goes over to the bar graph display on the right before heading off to the enclosure. Finally, there's a bank of 4 switches which provide the ALU function code on switches 1, 2 and 3, and then switch 4 loads a condition register. There's also 2 pairs of crocodile clips which bring power in from the power supply and pass it on to the enclosure. The power leads head behind the enclosure and then over to the power supply on the far left. As always, I'll start with switching the power supply on, and currently with all inputs off, the no operation LED is lit, and all 8 bits of the not B logic result are lit. If I quickly load the condition register, it will show the 0 state as expected. So, diving straight in with a real-world example, I'll add 100 and 200 together. Next, I'll perform 100 plus 1 by using the increment B function. I'll now try running through the logic functions, so I'll set up the usual on-on, off-off and on-off, on-off patterns on register B and C respectively. And then set the function code for each function in turn. It's worth noting, of course, that for the not B and shift left B operations, the value on register C is ignored. To demonstrate that, I'll clear register C and show shift left again. While I've got the registers in this state, I can actually load register C with the result coming off the ALU, although this of course is only valid when the input of C is being ignored. In this case, when I tried loading B with the result of the ALU, which itself was being fed by register B, all bits were lost. Generally, register B and C should never be loaded from the ALU result, as odd things can happen. One dramatic example of that is setting the increment B operation on the ALU and then loading register B. As you can see, the feedback in this case causes the relays to oscillate on and off rapidly, which would eventually cause the relays to burn out. The instruction set for the computer only allows results from the ALU to be loaded into the upcoming A and D registers, thereby ensuring these sort of feedback oddities can't happen. Next up, I'll attempt to consume as much power as possible by setting all bits on register B and C and then selecting the Add ALU function. As you can see, that's coming in just under 1.6 amps, which actually isn't too bad over 4 cards. Finally, I'll demonstrate an example where I can count up from 0 by using the incrementer to load register C, and then copy the result back to register B and perform the increment again. Again, this is something you wouldn't be able to do when the computer is complete, but you'd achieve the same thing by using registers A or D. So, that's it for now. Next up will be the A and D registers, so that we can start to do some running calculations with the ALU. This will be the last of the 5 Z backplane cards, and so it'll be time to start working on cards for one of the other 3 bays in the enclosure. Please visit my blog at relaycomputer.blogspot.co.uk to see more information on this card and the ongoing construction of my relay computer.